In this video, we're solving a classic conservation of angular momentum problem. We're given in the initial state a heavy rotating disk. It has a mass of 3.1 kilograms, a radius of 25 centimeters, and an initial angular velocity of 155 rotations per minute. So then we drop a smaller disk on top of this thing, and the smaller disk has a mass of 1.2 kilograms and a radius of 18 centimeters. And so we have what we could call a rotational collision between the two disks, and they end up coming to a common final angular velocity. And the first goal in the problem is to find that final angular velocity, and then we're going to compute the amount of energy lost in this collision. So you might remember for just linear momentum conservation, if you have an inelastic collision, meaning the two objects stick together, there's always energy lost, and we're going to see the same thing in this rotational collision. So to tackle part A, we're using angular momentum conservation. So we could say L initial is equal to L final. And our initial angular momentum is given by the initial moment of inertia times our initial angular speed. And in the final state, I have some final moment of inertia. It's larger because we added another disk. And then we have a smaller final angular speed. And then we can start to put in all the details about the initial and final moment of inertia. And so our initial moment of inertia, and I'm just going to keep this symbolic for now, is the moment of inertia of a heavy disk, and that's 1/2 mr squared. And I'm going to use a big M and a big R for this because it's the big disk. And I'll post a link to the video where that moment of inertia was first derived. In the final state, we have two disks added together, so we can just add together the moments of inertia. And I still have the big disk, that's 1/2 big M, big R squared, but I also have the small disk. And not surprisingly, I'm going to use a little m for that and a little r for that. So I have a 1/2 mr squared for that. And then my final angular speed, omega final. So one thing we can do to clean things up is just multiply both sides by 2 and get rid of all these factors of 1/2. And then we'll just symbolically solve for omega final. So when I isolate omega final, I get a big M, big R squared in the numerator. Big M, big R squared plus little m, little r squared in the denominator times omega initial. And we're ready to plug numbers into this thing. And one of the interesting things about these problems is that we can stay in these unusual units of rotations per minute. And this doesn't cause any problems for us. And I'll try to make that clear as we get to the final answer. But to answer part B, we are going to have to convert to the SI units here of radians per second. So we're going to answer this in both ways. So just subbing in our numbers. Big M was 3.1 kilograms, big R, 25 centimeters. I'm going to go ahead and convert that to meters. But even that is optional because I can see that my units of centimeters are going to cancel from the top and bottom of this fraction. Same thing in the first term for the denominator, 3.1 times 0.25 squared. And then my little m is 1.2 kilograms, and the radius there, 0.18 squared. And then omega initial was 155 rotations per minute. I'm going to go ahead and write that as a fraction, rotations per minute. So we can see this entire fraction is unitless because it has units of kilogram meters squared in the numerator and denominator. So when we run the numbers on this in our calculator, we're just going to get units of rotations per minute. So that's a fine way to state the final answer. And keeping 3 significant digits here, I get 129 rotations per minute. Okay, so we slowed down a little bit, and that's not surprising because if I go back and think about just from first principles here, angular momentum being conserved, well, what we did was turn up the moment of inertia. We made that bigger, and in order for this product to come out to the same value, the omega has to get smaller. So we were expecting that. Now, the last thing I want to do up here in part A is convert this to radians per second, because in part B, we're going to have to compute rotational kinetic energies in joules. And to do that, we need our rotational speed to be radians per second. So it's just a little unit conversion. I need to convert rotations to radians. So every rotation is 2 pi radians, and then minutes to seconds. So every minute, just putting that in the numerator, is 60 seconds down there in the denominator. And this gives me 13.5 radians per second for our final speed. So now in part B, we want to find the kinetic energy that was lost in this collision. So that requires that we find the initial kinetic energy, the final kinetic energy, and then the difference. And we're going to find out that there's a little bit missing. Before we can get that initial kinetic energy, we need to convert this initial angular speed of 155 rotations per minute into radians per second. So it's the same series of conversion factors. I have 2 pi radians for every rotation. I have 1 minute for every 60 seconds. And this gives me about 16.2 radians per second for the initial angular speed. So now we can get the initial rotational kinetic energy, and that's 1/2 I omega squared. So I initial, omega initial squared. And my initial moment of inertia is just the moment of inertia of that single big disk. So 1/2 big M big R squared, omega initial squared. And now we're ready to plug in numbers. So I have 1/4, just moving the two fractions together. And then my mass is 3.1 kilograms. My radius 0.25 meters. And this time we do have to use the conversion to meters because I need joules to pop out of this thing. And then my initial angular speed, also in SI units now, 16.2 radians per second, all squared. And this gives me about 12.7 joules of initial kinetic energy. Now the final kinetic energy is a little uglier expression because the moment of inertia has 2 pieces. So I have 1/2 I final omega final squared, and we just add together the moments of inertia of our 2 disks. So 1/2 big M big R squared plus 1/2 little m little r squared, omega final squared. And again, we can move the 1/2s together to create a 1/4. And we sub in all the numbers here. So 3.1 times 0.25 squared plus a 1.2 times 0.18 squared. And then our omega final squared. So that's 13.5 radians per second, all squared. And this gives me about 10.6 joules. All right, so we see a little bit of missing energy there. And I'll just call this K lost. That's going to be our initial amount, 12.7, minus the final amount, 10.6. And we see that we've lost about 2.1 joules of energy. And again, this isn't too much of a surprise because we're already used to this concept with translational momentum conservation when we're looking at inelastic collisions. It just turns out for 2 objects to move with the same final velocity, the only way to get that done is for some energy to be lost. And the same thing is true in the rotational context. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.